Hello everyone, I hope you're having a wonderful day. My name is Kyle Collins and I will be taking you through the 5th Physics 2211 lab. This lab is going to be a little different because I'm going to be able to choose what I want to do. In this video, I will go through the purpose of the lab, explain key concepts, show you the experiment and analyze a computational model using GlowScript, then I will show you results and explain, answer a question and conclude. In this lab, we are going to examine the motion of a falling slinky, and we will use tracker to determine if the bottom of the slinky stays motionless. After that, we will compare the predicted model and observed model. We will know the predicted path by using Newton's second law and many other factors, and we will compute that using GlowScript. So, key concepts. First, we're going to need to know the momentum principle, better known as Newton's second law. In every lab, Newton's second law was important, and in this week it will be a key factor as well. The law states force applied to an object is directly proportional to the rate of change of its momentum, and it occurs in the direction in which the force is applied. We know this as force equals mass times acceleration. We also can derive F net equals change in momentum over change in time. F net equals F grav plus F drag plus F slinky. Next, we need the velocity update formula and position update formula, which will be in our code when we're looking for the position of the slinky. We know that gravitational force is going to be negative mass times gravity plus j hat, which is the direction of the slinky in the y direction. Next equation we need is the drag force equation, which is our drag constant times velocity squared. Lastly, we know that tension is the absolute value of the gravitational force. In this lab, we know the mass of the ball is 0.25 and the system is the slinky, earth, and gravity. It has no surroundings. Here is the video of the man dropping the slinky in slow motion. As you can see, the bottom of the slinky remains motionless when it is dropped until it is fully compressed and falls down to the ground. Here is our analysis of the video. The total time of the clip was 8.687 seconds from the time he released it to the time it touched the bottom. The initial position of the ball was 0, 0, 0 because I set that to be the origin point. The velocity would also be 0 because it was not moving. The delta t is 0.001 because that is the time between each frame. And we know that the drag constant is 2.6. To the right, we have the position versus time graph, which is downward sloping curve, which shows the bottom did not move until it was fully compressed. Here is our computational model. Even though it says ball, just ignore that. It is supposed to be slinky. Our slinky mass is 0.25 as stated earlier, and the position is 0, 0, 0, and velocity is 0, 0, 0 stated from the previous slide. Our gravitational constant is 9.8 because it is the gravity of the Earth, and constant drag is 2.6. In this next part of the code, we got to do a while statement, so I put the time it took when the slinky first started moving, which was 5.933. Next, we have our equation for our gravity force and our tension force, and we just add those to get F net. We also have the velocity update formula and position update formula. However, it should be 0 because nothing has changed until this time. The last section of code is between when the slinky is moving and touches the ground. We had to change the drag force equation here to be the equation we found in our equation slide. And we also had to keep our velocity update and position update formulas to track the position of the bottom of the slinky. Here are the graphs side by side. On the left, we have the graph of the GlowScript code, and on the right, we have the graph of the data from the experiment using tracker. As we can see, both graphs are pretty similar, so we can conclude our experiment turned out to be successful. However, since they do not look identical, we know that something had to occur to make it be stutters in the experiment graph. For example, it could have been me mistracking the bottom of the slinky, or it could have been wind or something moving the slinky. But in this one, we didn't have to account for real-world errors. So a question you may be asking is, why does the slinky bottom not move? Well, because of the delay in the tension and compression waves throughout the coils, with the bottom end only beginning to move once the waves reach it. So This means Slinky will only move once it's compressed because of the way it's fallen. Thank you for watching this lab. I really appreciate you all throughout the year. I hope you learned something this semester.